Welcome. So, like I promised in the last module we have seen the integrated differentiator, and this module we will see a very important application of operational amplifier, that is your filters, right. So, when you talk about filters, what comes into picture, right, what comes into your brain first, what comes into your mind first. If I say filter, what do you mean by filter? Do we have filter in our body? Can we see anything that we have filters, right? So, think about it, right. Is my eye a filter? Is my nose a filter? My mouth a filter? Is it or not? Think about it. And if there is a filter, what is the role of this filter, right. So, to keep it extremely basic, filter is nothing but it will be removing the unwanted signal, right. When you talk about electronics. So, let us take an example of a tea, right, that I told you in the first lecture. So, when you prepare the tea, finally you have to filter out the tea and only filter out the milk, right, and the tea and the remaining substance you take it in the filter, that is also a filter. So, finally you get the liquid tea without the tea seeds. So, that is also example of a filter, right. So, filters can be of several types, but when you talk about electronics, when you talk about filters, then it is a system or it is a circuit that can be used to remove the unwanted signal, alright. So, when you talk about electronics, it is a circuit that can be used to remove the unwanted signal. Now, how we can fabricate or how we can design these filters, and what are the kind of filters that are used in analog electronics. So, we talk about several filters starting from a low pass filter, then we will see a high pass filter, then we will see a band pass filter, then we will see a band reject filter. For today's module, we will just understand what are filters and then what exactly is a low pass filter, alright. This is the idea for today's module, and once you are able to understand low pass filters, then you will go to the breadboard and we will see how we can actually design the filter, and how can we see different parameters, or how we are looking at the performance of the filter. Now, when I talk about filter, we should also understand whether it is a passive filter or is an active filter. So, what exactly a passive means? So, if you remember, I have told what are passive and active components somewhere in my this series of lectures. But to quickly understand, a passive component is a component which will not require any external source to drive it, alright. The active components are the components which requires external source to drive it. For example, if I take a resistor or if I take a capacitor, it is a passive component, right. If I take a op amp or if I take a transistor, if I take a MOSFET, right, it is an active component, alright. So, without applying voltage or without applying the bias to the op amp, can you use it? No, right. Without applying the bias or voltage to the transistors, can you use it? No, right. What about resistors? Does it require? No, just put the resistors in between, it will start working. So, the point is active, passive, right. So, what are the passive filters? What are the active filters? That means passive filters are the filters designed from components which are passive. Active filters are filters that are designed from components which are active. That means it will be a integration of active and passive components, right. So, let us see one by one what is filter, and then we will understand the concept of the filter. I have already told you the concept of filter in theory class, but like I do in my experimental classes, I am repeating what I have taught you already in the theory, alright, just to help you to refresh it quickly, alright. So, if you come to the screen, what you will see is the introduction to the filters. Now, we have already seen filtering removes unwanted noise from signal measurements after they are amplified and presented to A to D converter. What does that do? Frequency filtering removes unwanted noise from the signal measurements and they are amplified, So, let me give you an example. Okay. So, I have this breadboard, right. You can see in my hand I have a breadboard with lot of components on it, right. There is a resistor, there is a LED, there is a op amp, there is a wires, there are wires, right, connecting wires. And now I say that you have to design a filter such that it will only consider this as a signal, this LED as a signal, and remaining thing as a noise. So, you understand that remaining components on these breadboards are noise, and only LED that you see here is my signal. Only LED that you see in my on my breadboard is a signal. So, how to design something that can consider this, if you take a image, right, because for you right now this is nothing but an image. So, if you have the image, from the image how can you understand, how can you remove the background noise, and how can you lift up the signal, right. That is what we do in what CMRR, right. That is why we require high CMRR, common mode rejection ratio. We increase the signal, we reduce the noise. Same way, if you want to reduce the noise, this is just a crude example, do not take it as a actual example. I was just showing you that if I have the LED as a signal and remaining thing in your image as a noise, how can I remove the noise and how can I consider only the signal, alright. So, coming back to the electronic application, in electronics when you talk about noise, it is the unwanted signal, and we talk about signal is something that we want information from, right. So, what does that mean? What does that mean? So, I had shown you one experiment yesterday. Let me show it to you. If we can get quickly video audio continuously that makes a particular sound. Let us see if we can get an audio that can continuously make a sound, and in between that sound if there is a signal, can we identify that signal or not? That is a noise, right, even noise. So, by the time we get this audio, let us see the next thing, and let us check it. So, ideally we will see the example of this noise, okay, unwanted noise, and we will see example of this signal. I will give an example. So, right now let us see the second point, which is this one. Ideally filter should eliminate all data at frequencies outside the specific frequency, right. What is that? Filter should eliminate all the data at frequencies, that is desired frequencies, outside the specific frequency, right. Ideally filter should eliminate all data at frequencies outside the specific frequency, alright. You have to remember this thing which is about the filter. So, what does that mean? That if I select a frequency, let us say FC, alright, then except this frequency the data from other frequencies should be eliminated. That is my ideal filter, alright. That means it should eliminate all data at frequencies outside the specified frequency, range, providing a very sharp transition between the frequencies that are passed and those are filtered out. You got it? So, the point is that what are filters? Filters are nothing but a circuit that can be removed, that helps to remove the unwanted noise from the signal. Second, this ideally filter should eliminate all the data at frequencies outside the specific frequency, providing a very sharp transition between the frequency that are passed and those are filtered out. That means, let us say that we will have a different graph. We will see that the frequency that above this are all filtered out, only these frequencies are passed. In this case, the frequencies above this frequency are passed, below this are all filtered out, alright. So, this transition that it makes suddenly, right, this should be extremely sharp, this transition should be extremely sharp. That is what we are talking about when we talk about the sharp transition between the frequencies that are passed and that are filtered out, alright. Now, let us see the fourth point or third point. Most practical filters are not ideal most practical filters are not ideal and do not usually eliminate all the undesirable amplitude components outside a specified range of frequencies, outside a specified range of frequencies. That means that ideally we want that it should only selectively select the frequency that we require and eliminate all the other frequencies. But when you actually fabricate a filter, actually design a filter, then what you find is that it usually do not eliminate all the undesirable signal. That is ideal case, that is a practical case. Ideal case, all the undesirable signal will be removed, practical case undesirable signals may not be removed, alright. So, attributes of common filters or attributes common to filters, attributes common to filters are A, cutoff frequency, B, roll off, and C, quality factor. Very important, extremely important. Why? Because when you talk about filters, generally you will be asked this kind of question: do you know what is the quality factor of your filter? Do you know what is the cutoff frequency of your filter? Do you know what is the roll off rate of your filter? So, in that case you have to find it out what exactly cutoff frequency would be, what exactly roll off would be, what exactly the quality factor would be. So, you should understand these three attributes extremely by focusing to this particular lecture, alright, and also see once again the theory class that we had where I have taught you what exactly cutoff frequency, roll off and quality factor means. Okay. Now, what we have seen until here, what we have seen first is unwanted noise from signal measurements, that is a roll off filter. Second is it should eliminate all the data frequencies outside the specified range of frequencies. Third is it should have a very sharp transition between frequencies that are passed and those are filtered out. Fourth is the ideally they do not usually eliminate all the undesirable frequencies. This is what we have understood about the filters. Then we have seen attributes common to filter, three attributes: cutoff frequency, roll off and quality factor, alright. Now, what is the next one? Next one is almost all communication systems use filters. You see, that is why the filters are extremely important. All the communication systems use filters, all the communication system use filters. Now, if you see and if you hear this, okay. This is, you see, there is a rain on the background and you can see the flute playing in the front, right. So, you can consider the falling of rain, see, you can see the rain is falling, right, not actually, you can see, you can hear it, and a flute is there playing. Once again, okay. So, what you are looking at? You are looking at the rain in the background, right, and there was a flute as a as somebody playing flute. So, what we understand from here is, if you want to consider the noise of the rain, right, this raindrop as a noise signal, unwanted signal, and flute as a signal, then you can increase the signal and reduce this noise by using the filters, You can also do the similar thing by adjusting your CMRR, alright. So, anyway, coming back to the filters, the main advantage or the main application of filters is in communication systems. So, almost all communication systems, you see, almost all communication systems uses filters. So, a filter passes one band of frequencies while rejecting another. A filter can be passive or it can be active. This I have already discussed. right. There are active filters, there are passive filters. So, what is that? A filter passes one band of frequencies, all right, while rejecting another, and a filter can be passive or it can be active. Okay. Next, what is next? Filters are built with resistors, capacitors and inductors. Okay. That means, we use these passive components for designing the filters. Which are passive components? Resistors, capacitors and inductors. They are generally used above 1 megahertz, have no power gain and relatively difficult to tune. Okay. Which one? Passive filters. Which one? We are talking about passive filters. Passive filters are built with resistors, capacitor, inductors. They are generally used about 1 megahertz and have no power gain and relative difficulty to tune. No power gain because there is no op amp, no transistors, no active components, and there is no feedback. We cannot change the gain. There is no power gain. It is difficult to tune, and it can also not be used at, generally they are not used at extremely low frequency, right. Now, active filters are built with resistors, capacitors and operational amplifier. You see here. So, if I just remove everything, one thing that you can see a difference between active and passive is active and passive. One main difference is your op amp, right. Again we come back to the same point, operational amplifier, all right, and they are useful below 1 megahertz, one good thing, have power gain, excellent, have relatively ease to tune, amazing, right. So, that means that when you are given a choice of using active or passive filters, try to use active filters, that should be the goal, all right. So, quickly let us again see this screen, and again quickly let us recall what are filters. Filters are a circuit, or they are circuit which are used for removing unwanted noise from signal measurement. 1. Second, filters should eliminate all data outside the specified frequency, providing a sharp transition. 2, right. Third, most practical filters are not ideal and do not usually eliminate all the undesirable frequencies. Fourth, there are 3 attributes common to all the filters: cutoff, roll off, quality factor. Fifth, almost all communication systems uses filters. Sixth, a filter passes one band of frequencies while rejecting another, right. Seventh, passive filters and active filters. Passive filters are made of resistors, capacitor, inductors, cannot be used below 1 megahertz, or can only be used about 1 megahertz, or cannot be used below 1 megahertz, have no power gain and relatively difficult to tune. Active filters are built with resistors, capacitors and op amps, and they are useful below 1 megahertz, have power gain and can relatively easy to tune, all right. Very easy to understand and very important circuit, which is your filter. That is why I am taking little bit more time, so that you do not miss this particular circuit, because it is used in most of the communication systems. Almost all communication systems uses filters, all right. Now, let us see the next one, the attributes, all right. What is the first one? First one was cutoff frequency. So, what exactly cutoff frequency is? Again we have seen this cutoff frequency in theory, but let us again quickly see what is cutoff frequency, all right. So, this is the transition frequency, at which filter takes effect. That means, at this particular frequency the filtering actually takes into effect. It may be high pass cutoff or low pass cutoff frequency, and usually defined as the frequency at which normalized gain drops 3 dB below unity. Very important, again the same thing I told you in the theory. I am talking to again to you in the practicals, that why you have to use 3 dB the 3 dB below unity. Why? Right? Why it is said that defined as a frequency at which the normalized gain drops to 3 dB, normalized gain from here drops to 3 dB below unity. Why? Why 3 dB and not 8 dB, 10 dB, 15 dB? What is the role of this? Find it out. Alright. So, very important sentence, very important for you to understand, and like I said, I will not explain you, I am not going to explain you here, you have to find it out, right. I am not here to provide you spoon feeding, no spoon feedings. So, try to find it out. If you try and you do not get the answer, then you ask, then you are free to ask in the forum, you are free to ask whatever you have, any questions you are free to ask, but first please try. Alright. Second attribute, what second attribute? Roll off, right. This is the slope of the amplitude versus frequency graph at the region of the cutoff frequency. So, you will see in the next graph, you will see that actually ideally it should be like this, right. For example, the high pass low pass filter. So, low frequency will pass, high frequency will not pass, you will see ideal curve like this. What is ideal curve? This is amplitude, this is frequency, right, x axis, y axis. Now, what is roll off? This is the slope of the amplitude versus the frequency graph at which the cutoff frequency. This is ideal situation. Practically you will have situation like this. Alright. So, this slope that you see is a roll off. Alright. This slope, see, slope of amplitude versus frequency at region of the cutoff frequency, here at the region of the cutoff frequency, right, will give you the roll off of the filter, This characteristics distinguishes an ideal filter from a practical or non ideal filter. Ideal filter, it should have sharp transition, right. Practical filters may not have sharp transition. So, that this roll off thing distinguish your ideal from practical, this is what it says, alright. So, when you understand, when you really read carefully, you can understand any kind of course. So, it is just about reading with concentration, alright. So, this characteristics distinguishes an ideal filter from the practical one. The roll off is usually measured on a logarithmic scale and units is decibels, units of decibels for what? Roll off. Now, the second question which I asked again in the theory and I am again asking you in this experimental class is why in decibels? Why? What is a why roll off is generally measured in log scale and why units is in decibel? Is there any reason to measure in log scale, right? Why we have to bother ourselves with log scale and decibels and this and that? What is the role of measuring in log scale? Alright, find it out. Try your best. If you do not understand, ask. Alright. Third thing, quality factor. This variable is an adjustable characteristics of a tuned filter and determines the gain of the filter at its resonant frequency as well as the roll off rate or roll off transfer characteristics on either side of resonant frequency. So, very important, here you can tune the quality factor and it will determine the gain of the filter at its resonant frequency as well as the roll off rate or roll off transfer characteristics on either side of the resonant frequency. What exactly resonance means? What is resonance? Physics, right? Understand what is resonant, right? When two frequencies we can say it is resonant with each other, right? Understand. When you understand these terms, it will easy for you to understand three attributes. First is cutoff frequency, roll off and quality factor. Alright. So, I am hoping that you have attended all the theory class, and now you are again refreshing the same attributes which I am teaching today. So, your concepts would be little bit more clear than it were earlier, alright. Okay. Let us move to the next slide. So, now you see, if you see here, what you see is that if I use a filter, right, if my input signal is this, you see input signal is this, if I use a filter, I can remove the unwanted signal, remove this unwanted this noise and get a better signal at the output, a filtered signal at the output, right. So, what is filtering? Certain desirable features are retained, other undesirable features are suppressed. You see, suppressed, bold, that is why you see we have used two different way, retained, bold, in bold, suppressed, bold, right. Then what is retained? If you see this one, this is let us say x, this let us say y, if you see these signals, the signal that we are interested is this one, that is why this particular signal is retained, while this noise, the spikes here that you see, right, this one you see here spikes, lot of spikes, these spikes are not here, they are not here, right. That means we have removed or we have suppressed the spikes, that is our undesirable features, alright. So, with the help of filter we can retain the desirable signal, we can filter out the suppressed or we can suppress out the undesirable signal. Now, these filters can be active, can be passive, can be low pass, can be high pass, can be band pass, can be notch or band reject, and the today or this module is focused on understanding the low pass filters, alright. So, let us see the next slide. What do we see here? What we see here is how the filters, signal filters are divided into several categories, It is like a flow chart, not exactly flow chart, it is a divisional chart, that you can subdivide your filters into several divisions, and based on the application you can select that particular filter, alright. Now, what we see here, signal filters, two types, one is digital filter, another one is analog filter, right. We are interested in analog filters, If you talk about analog filters, further it is divided into two branches, as you see, element type, frequency band, based on frequency band. If you talk about element type, then either it is active or it is passive, because what elements are used in active, we know what elements, op amps, resistors, capacitors, passive resistors, capacitors, inductors, right, based on element type. Based on frequency band, right, which frequency it will allow to pass, which frequency it will reject, which band of frequency it will allow to pass, right, based on that, or it may allow all the frequency to pass. So, that means if it allows the low frequency to pass, we will say it is a low pass filter. If it allows the high frequency to pass, we will say high pass filter. If it allows band of frequency to pass, we say band pass filter. If it allows only one particular band to reject, rest of the bands to pass, band reject filter. If it allows all the frequency to pass, all pass filter, right. Extremely easy to understand filters in this particular way, alright. It is not so easy to understand the circuit, though I will try to make it as simple as possible. But if somebody asks now that, okay, do you know what are signal filters, can you tell us how they are divided, what are the further analog filters are divided into, then you can easily say yes, my answer is yes, I know signal filters signal filters into two different division. One is analog filters, one is digital filter. For the analog filter, based on element, it is either active or passive. Based on frequency, it can be low pass, high pass, band reject and all pass, right. Now, you guys know what are the classifications of filter. One more thing that we understood, okay, excellent. Now, we know signals frequency filters are classified into several categories. Then we have to see each category, and we have to also see active and passive, and we will perform experiments for each categories, alright. That means, we will use active and passive. So, let us start with a low pass, right. We will start one by one. Today we will see low pass, we will see active filter, we will see passive filter, alright. Then we move to the next module, we will see other band pass filters, high pass filters, all pass filters, band reject filters, alright. So, let us move to the next slide. Like I said, today this particular module we will see low pass filters. So, what are low pass filters? Low pass filters are also called high cut filters. High cut filters, right. Now, I have asked this question to few of my students in my class, and I asked that okay, quickly draw the circuit for high cut filter, and lot of students they have drawn the circuit for high pass filter. So, the reason is they knew that it is, they knew how to draw the circuit. It is not that they do not know, they know everything, they know high pass filter, band pass filter, they can draw in 2 minutes. It is not about testing their technical knowledge, is about testing their focus, right. How, whether you are learning it, whether you are reading the question, or you are assuming that you know everything, let us write immediately, right. So, make sure that when you are asked a question in an interview that draw a high cut filter, do not start drawing a high pass filter, understand, listen, right, process it and then draw. High cut filter is low pass, right, low cut filter is high pass. So, do not get confused, alright. So, again high pass filters, there are first order, second order filters, we will not go into that much complications for now, we will just see high pass filters and low pass filters. Today we are learning low pass filter, alright. In low pass filter are also called high cut filters, alright. So, if you see the circuit or if you see the graph here or the slide, what we see? We see the figure number 10, right, shows the ideal frequency response of low pass filter, ideal frequency response of a low pass filter. That means, you see here from 0, right, it is if this is a frequency, let us write down here, see this is a frequency, right, this is the amplitude, that means y is amplitude, x axis is frequency, alright. Now, that means it will from 0 hertz to some hertz low frequency, alright. This is our cutoff frequency FC, alright. So, the figure shows the ideal frequency response of a low pass filter. It is sometimes called a brick wall response because the right edge of the rectangle looks like a brick wall. You all have seen the brick wall, right. So, you see this one, alright. Let us do little bit of study. What is this? This looks like a brick, isn't it? So, this is me, I am running here, I reached here, I am running further. What will I do? I will hit myself against this wall, right, against this wall. Another way is I can jump, but I cannot jump because this wall is amplitude is long, I cannot jump, right. So, this is like a brick, I will hit myself against the brick, it is a brick wall. So, there is only one way that we can remove this brick wall, there is a way to remove this brick wall is by changing the filter, by changing the cutoff frequency, right. If I have to move further inside, I will design a filter with a cutoff frequency this much, and I can run till here, or another way I can stop at this point. Both ways okay, right. So, if you do not consider this example, this is just a example just to understand, okay. Do not consider and do not give this kind of example in the interview, that I am there and I am running against the wall and I hit myself against the brick wall, then you you really have to go and hit yourself against the brick wall, because you will not be selected. So, do not give this kind of examples in interview. This is just for you to understand and you to lighten up yourself when you are understanding some lectures, okay. So, do not give this kind of example. I am just giving it to you so that you get the idea, alright. So, the point is, if I change the cutoff frequency from here to here, that means then frequency that I am passing from here to here, this pass band will be narrowed down. This pass band will be narrowed down. You see this pass band compared to this band, right. So, this band is bigger, that means lot of frequencies can be passed. This is smaller, comparatively less number of the frequency range is less, right. Both is low pass filter, both is low pass filter. Since this filter response is, it looks like this particular response looks like a wall, we also call this one as a brick wall response, alright. A low pass filter passes all frequencies from 0 to cutoff frequency, that is what I said. This is cutoff frequency, this is 0 hertz, right, FC of particular hertz, right. So, this is your cutoff frequency, So, a low pass filter passes all the frequencies from 0 to cutoff frequency and blocks all frequencies above the cutoff frequency, alright. So, you see here, where is my FC, my FC is, or cutoff frequency is here, this one, right. Actually this is amplitude, so we can always say this one, right. Now, the frequencies that are not allowed above the cutoff frequency, the frequency which are not allowed above the cutoff frequency, right, this is called stop band, this is called pass band, right. Frequencies are allowed to pass, frequencies are not allowed to pass, or they are stopped. So, all low pass filter passes all frequency from 0 to cutoff frequency and blocks all frequency above the cutoff frequency. It will block all the frequencies above this cutoff frequency, alright. This is the case when we are talking about the low pass filters, alright. Low pass filter or high cut filter, alright. Remember. Okay. So, let us move to the next slide. And see a low pass filter with passive components, Now, this is how can we define this? This is elemental way of differentiating the filters based on R and C. Since we are using R and C, we say that this is a low pass passive filter, not because R and C we are using, we say low pass. I am just showing that if it is passive filter, we are using R and C, right. It is a low pass passive filter, that is why we have the circuit in this particular configuration. We will see why this configuration is used, which is your resistor and then you have capacitor, alright. So, a simple passive low pass, RC low pass filter, or people also write down LPF. For low pass filter they write LPF, for high pass filter they write HPF, for band pass filter they write BPF, right. So, these are also terminologies that you will find in different work, alright. So, do not get confused if there is a LPF instead of low pass filter. They also write RC low pass filter, RC low pass passive filter, alright, can be made by connecting together a series or single resistor with a single capacitor as shown in figure 11, alright. In this type of filter arrangement, the input signal V in is applied, you see this is input signal, V in is applied to series combination of series, this is in series combination of resistor and capacitor, but the output signal V out is taken across the capacitor only. You see here is taken across the capacitor only, alright. So, when you talk about low pass filters using passive components, it becomes low pass passive filter, and in that you have resistor at the input in series with capacitor. The signal is applied to the series of resistor and capacitor, and the output is taken across the capacitor, alright. This type of filter is generally known as first order filter or one pole filter, alright. This is another thing that I just discussed little bit before, that there are second order filters as well, there are multi-pole filters as well, 2 pole filter, 3 pole filter, second order filter, right. So, why first order or single pole? Why first order and why we have to use first order and single pole? Because, so why it is called first order or single pole, that is a question, alright. So, because it has only one reactive component, right, the capacitor in the circuit. What is reactive component in this circuit? Only capacitor, that is why one pole filter or first order filter, alright. And this first order filter will give you a if you talk about this kind of circuit, this kind of circuit also gives you a phase shift. If you really want to understand the phase shift, which we have studied in oscillators, right, 1 RC will give you a phase shift of 90 degree. If you adjust the value of R and C, you can change it to 60 degree, right. We have studied RC oscillators. In oscillators, how many RC were there? 3R and 3C or 3R and C, right, and then each one gave us how much degree of phase shift? Each one gave us 60 degree of phase shift. So, we had 3 RC, that means we got 180 degree of phase shift as a feedback to the oscillator, the feedback circuit to the oscillator. So, anyway, here what we are looking at, here we are looking at the 1 R and 1 C, because there is one reactance, only one component which is reactive component, that is why we call this particular filter as one pole filter or first order filter. Okay, cool, alright. So, next let us go to the next slide. So, if I now talk about op amp based active low pass filter. So, earlier what we were using? We were just using this particular section, right, we are using just this particular section, we were not considering op amp. This becomes your low pass and it becomes your passive. If I use op amp, along with the passive, right, it becomes my active filter, right. And what is this? This is nothing but your unity gain amplifier, favorite unity gain amplifier. We have seen the unity gain amplifier in the previous modules, and we could see it is so easy to operate, super easy to operate, right, and very important component when we are understanding the loading effect, right. If you remember, we have used the unity gain amplifier or buffer for removing the loading effect, correct. Okay. So, if I connect the R and C with my op amp, which is unity gain amplifier, then it becomes my active low pass filter, alright. So, the most common let us see this line, most common and easily understood active filter is active low pass filter. It is very easy to understand, it is most commonly used for explaining the low pass filter, and its principle of operation and frequency response is exactly the same as those for the previously seen passive filters. We have not seen previously lot of filters, but we have seen the RC filter. So, if I want to really derive the equation, but the equation would be Fc equals to 1 upon 2 pi RC. This is the frequency cutoff frequency formula for the passive filter or low pass filter. And if I want to further understand, then what I will see, its principal operation and frequency response is exactly the same as those for the passive filter. The only difference this time is that it uses the operation amplifier for amplification and gain control, right. We have seen what we have seen in the passive filters. We have seen that in the case of passive filters you cannot change the gain and it is difficult to tune your passive filters. Second thing what we have seen is that it cannot be operated when it is less than 1 megahertz, right. There was case of passive filters. But when you talk about the active filters, then you integrate your op amp to R and C, and we see that now because of the integration of this op amp you can adjust the gain and you can also tune your filter, and this kind of active filters are used for frequencies about 1 megahertz, above 1 megahertz, okay, and also below 1 megahertz, both below 1 megahertz as well as above 1 megahertz, alright. So, let us go back to the slide. So, the simplest form of low pass filter, active filter is to connect an inverting or non-inverting amplifier, the same as those discussed in op amp tutorial. We have seen already op amps, inverting amplifier, non-inverting amplifier, we have seen some examples, right. So, it is nothing but the easiest way or simplest way of constructing the active low pass filter is by connecting it to an inverting or non-inverting amplifier. You can also connect to a unity gain amplifier, connecting to a unity gain amplifier. The same to the basic RC low pass filter, as shown in figure. This is basic RC low pass filter, we are connected to unity gain amplifier, we can also connect to an inverting amplifier, we can also connect to a non-inverting amplifier, alright. This is the case of unity gain amplifier, but that does not mean that every time your RC, this basic RC will be connected with only unity gain amplifier. It can be connected with inverting as well as non-inverting also, there is a possibility, or if you want you can use inverting amplifier as the active component, or you can also use non-inverting amplifier in case of the unity gain amplifier, alright. So, let us go to the next slide and let us see. Now, op amp based active low pass filter, if you want to see the how this op amp based active low pass filter works, let us understand, alright. So, what we see with amplification, the last time we had no amplification. Why? Because if you see unity gain amplifier, there is no amplification here, can you do any amplification? You cannot do any amplification, right. But if you want to do amplification, then you have to connect the op amp in the configuration which is shown here, right. The frequency response of the circuit will be same as that of passive RC filter. That means that FC is 1 upon 2 pi RC, frequency response, done, except that the amplitude of the output is increased by pass band gain AF of the amplifier, alright. That means the amplitude can be changed by the gain of the amplifier. Gain of the amplifier you can say, you can select from here. This is a non-inverting amplifier, right. So, we have a formula 1 plus R2 by R1 is very easy into V in. If you want to just see V out, what is V out, then only for non-inverting amplifier it will be like that. For non-inverting amplification circuit, the magnitude of voltage gain of the filter is given as a function of feedback resistor R2 divided by its corresponding resistor R1 value, and is given as follows. This is the DC gain of this particular non-inverting amplifier. I have said this hundreds of times, what is the DC gain of a non-inverting amplifier, what is the gain of an inverting amplifier, right. So, you should now remember this formula by heart, alright. So, quickly if you see what exactly this op amp based active low pass filter is, then what we see is it is nothing but when we connect the RC, when we connect R and C in this particular fashion to the non-inverting amplifier, then we can see that it will filter out, it will filter low frequency based on formula F equals to 1 upon 2 pi RC, and it will also increase the amplitude. You see signal here, if I see peak to peak voltage, and if I see peak to peak voltage here, then there is an increase in amplitude. This increase in amplitude is given by the non-inverting amplifier, alright, non-inverting amplifier. So, low pass filter stage, high frequencies, low frequencies, amplification, output, cool. Now, if we have learned this much, then we should be able to do the experiments as well, right. So, this particular circuit and a little bit of the information is taken from electronics tutorial.ws. I have already given this thing from wherever I try to use the images, right. I to give you I tried to put the acknowledgement on the slide, so that you should also learn that when you use some material and you use it for tutorials, like to teach students, it is okay, but still you should acknowledge the work that is done by somebody else, right. You should not claim as it is your work. So, even when my student, right, or a TA, he makes a circuit, for example, Sitaram made a circuit using PSpice, I said that he has done this particular work. You should always try to give acknowledgement, you should always try to acknowledge the work done by others, right. So, that is a good way of understanding the things, good way of learning the things, good way of performing the experiments, good way of understanding different subjects, and that is a ethical way of working or studying any particular subject or working in the laboratory. Alright, always try to acknowledge, always try to give credit to people who have done the work, and if you miss out because of some kind of like your own mistake, once in a while it is okay, but try to be focused and try to acknowledge from wherever you take the material. Alright, okay. So, as and when it is possible, I always try to tell other things which are very important as an engineer that you should follow. That is why this is one of the things that you should understand, that you should acknowledge the efforts by others. Alright. So, we will see the we are continuing the same module, which is op amp based active low pass filter, and the gain of the first order low pass filter is given by V out by V in equals to AF under root of divided by under root of 1 plus F by Fc whole square. This we have seen. Now, here what will happen? Here what will happen? AF is the pass band, this AF is the passed band gain of the filter is given by 1 plus R2 by R1. Why 1 plus R2 by R1? Why pass band gain is given by this particular formula? Because we are using non-inverting amplifier, right. We are using non-inverting amplifier, that is why this is the formula. So, that is why we have given AF equals to 1 plus R2 by R1. Okay, excellent. Now, second, F is the frequency of the input signal in hertz, this one. Alright. Third, Fc is the cutoff frequency again in hertz. Frequency is given in hertz. So, F is a input signal in hertz, Fc is a cutoff frequency in hertz. Now, what will happen when very low frequency is there? When very low frequency is there, F is less than Fc. That gives us V out by V in equals to AF. How? See, F is extremely low compared to Fc, then this component becomes this component. Let us see, F is extremely low, right. F is less than Fc, that means this component becomes 0, right. So, AF divided by 1 plus 0, AF divided by square root of 1, right. So, that is how we get this particular equation. If we go for the second one, which is the cutoff frequency, at cutoff frequency F equals to Fc, we find AF equals to V out upon V in equals to AF by under root of 2, which will give you this particular value. At very high frequency, when your F is greater than Fc, in that case we will find out V out by V in is less than AF, So, this you have to remember when you are understanding the active low pass filter. We will see in active high pass filter similar kind of things, but this will get interchanged with this, like this. We will see, alright, we will see, do not worry about it right now. Right now, you just think and listen to what I am saying is at low frequency F is less than Fc, you get this particular value. At cutoff frequency F equals to Fc, you have this particular value. When you have high frequency F greater than Fc, you have V out by V in less than AF. Alright. So, until here I hope that it is extremely clear what is low pass filter, what are the passive low pass filter, what is the active low pass filter, what is the formula, and how we can move forward. Alright. Now, let us see the example. So, if I give you an example, right, or if somebody asks you an example that you have to design a non-inverting active low pass filter circuit that has a gain of 10. Alright. So, I will already write AF equals to 10, gain of 10 at low frequencies, a high frequency cutoff or corner frequency 159 hertz, that is also given, and an input impedance of 10 kilo ohms, input impedance of 10 kilo ohms, this is given. Alright. Now, we have to design the non-inverting active low pass filter. So, what is AF for non-inverting? AF equals to 1 plus R2 by R1, which is given, which is 10. Right. Now, assume a value of R1 to be 1 kilo ohm. If we assume value of 1 kilo ohm, rearranging the formula above gives R2 of if I rearrange this formula, R2 will be 10 minus 1 into R1 or 9 into R1 which is 1 kilo ohm or 9 kilo ohm. Now, I have R1 which I have assumed of 1 kilo ohm, R2 I got 9 kilo ohm. If I have both the values, then for voltage gain of 10, R1 is 1, R2 is 9, however 9k resistor does not exist. So, next preferred value is 9k 1 ohm. What exactly 9k 1? What does that mean? 9k 1 ohm. What do you mean by this? Alright, understand what is that? Alright, is used instead of 9 kilo ohm. Instead of 9 kilo ohm, I am using this value. Why? Converting this voltage gain to decibel gives us value of 20 dB. Gain in decibel we have getting 20 dB. So, now we have value of R1, R2, we have value of gain, and we can design the filter. If we continue further, because this is just we have find R1 and R2, that means we have find the value of R1 and R2, right. We have found the gain which is 10. Okay. Now, what? Now, we have this formula, right, which is the formula of the cutoff frequency. The cutoff frequency or corner frequency is given as 159, is already given 159 hertz. So, that means that Fc equals to 1 upon 2 pi Rc, where Fc is 159 hertz and R equals to 10 kilo ohm, right. So, again if we rearrange this thing, we can get C equals to 1 upon 2 pi Fr, right. So, if I put the values 2 pi, Fc is 159, R is 10, I get value of C as 100 nanofarad, I get value of C as 100 nanofarad. That means now I can design this circuit with R equals to 10, C equals to 100 nanofarad, R1 equals to 1 kilo ohm, R2 equals to 9k 1 ohm. Why? Find it out, 9k 1 ohm, and we have to calculate, we have to understand what is V out. So, when you see you will find that if I draw the decibel gain versus frequency, and the gain is in decibel, then gain will be 20 log V out by V in, right, and I will have cutoff frequency somewhere here. I have a slope of minus 20 dB by decade. You know that if I use 1 RC or single pole, I have minus 20 dB. If I use 2 double pole, it will be minus 40. If I go on increasing, I will get this particular slope close to my ideal value. It will just go down, come closer and closer and closer. Alright. So, from this what we got is, we understood now that now with the formula that we have, we can design a low pass filter. So, let us take another example. And here if you see a circuit, right, again this circuit is prepared by Sitaram using PSpice, and what he has done, he has said okay, if you want to design a non-inverting active low pass filter circuit that has gain of 10, at low frequencies, a high frequency cutoff or corner frequency of 1 kilohertz and an input impedance of 10 kilo ohm. For this given set of values, what will be R1 and R2? So, if you solve, you will find R1 equals to 1 kilo ohm and R2 equals to 7.1 kilo ohm. This is, you can take an example or exercise problem and you can find the value. You will see that you will arrive at this particular value, R1 equals to 1 kilo ohm, R2 equals to 7 kilo ohm. This is kind of solution for you, solution, alright. This is your question. Okay. So, if you take this particular circuit, this is your low pass active or active low pass filter, right, and these are bias voltage, again like I said, right. You have capacitor, you have feedback resistors, you have R3 at the input, right. So, it goes from here, you can adjust your gain using R2 and R1, that is what you have to find R2 and R1 in this particular problem, alright. So, let us come to the actual experiments and let us perform some experiments with low pass filter with passive and active components. So, when you actually perform this experiment and you see the signal, then you will find this particular slope, right, a fine slope here, and like I said that this will be your some cutoff frequency somewhere next to here, right, and you can find this slope nearby the cutoff frequency. You can understand whether it is a single this is a single order or single pole active low pass filter, alright. This is the amplitude, this is amplitude and this is frequency, this is frequency, alright. So, let us see some configuration. Now see, sometimes you will be able to see the circuit drawn in this particular fashion, in this particular fashion. Sometimes you will see the circuit drawn in this particular fashion, alright. So, again do not get confused, both are same circuits, both are same circuits. This simplified non-inverting amplifier circuit, this equivalent inverting amplifier circuit. Sometimes you see inverting amplifier circuit, sometimes you see non-inverting amplifier circuit, that does not really change the game, right. The result would be same, that we both are active low pass filter, right, both are active low pass filter. It depends on you which one you want to consider, it depends on you which one you want to consider. You can consider non-inverting, you can consider inverting, and you can see the change in the input and output, alright. So, now we will actually perform the experiments with the op amp based active low pass filter using the inverting amplifier filter circuit, alright, using this particular circuit. But before we use this particular circuit, that means that we are having an active component which is the operational amplifier, right. We have to first understand how just passive, RC filter will work or passive low pass filter will work, passive low pass filter will work. Then we will see active low pass filter, which is this one, okay. So, let us see how we can design it and let us see how we can move forward for the experiment part. Now, here we will be understanding the passive low pass filter, and in this we have to understand how the experiment would work, So, first we will understand how we can use or how we can study the working of passive low pass filter. So, here what we are using? We are using one resistor and one capacitor, right. Now, we have to connect the R and C in this particular fashion, So, connect the circuit as shown in figure on side, which is this figure. Here R equals to 10 kilo ohm, we have kept value T R equals to 10 kilo ohm, C equals to 10 microfarad, this is 10 microfarad. Now, we will apply 5 volts peak to peak sine wave at 100 hertz directly to the V in. So, where this is my sine wave, I am applying 5 volts and frequency is 100 hertz, So, if I apply 5 volts peak to peak, at a 100 hertz frequency sine wave to this particular circuit R with R and C, what kind of voltage I observe at the output, what kind of voltage I observe at the output, right. So, we have to observe the output voltage V out and note down its peak to peak output voltage, and then we also have to comment on the shape of the output signal. We have to do two things, right. First is when I apply 5 volts, right, peak to peak, peak to peak, peak to peak generally we can write peak to peak, or we are just saying 5 volts peak to peak. The frequency is 100 hertz as an input signal, to this particular filter, what will be the output voltage V out and what will be the shape of output voltage, alright. Let us do this. So, let me just clear it back so that it is easy for you to look at the screen when I ask, and look at the breadboard when I request the camera to focus on the breadboard. So, let us see the low pass RC or passive filter, alright, low pass passive filter. Okay. So, here if you come back to the screen quickly, so there is one change that we have done. Instead of C equals to 10 microfarad, we have used C equals to 0.1 microfarad. Okay. So, here my C would be 0.1 microfarad and my R is 10 kilo ohms, 10 kilo ohms, alright. So, understand this thing. So, now you see what is the voltage V out. Here I am also assuming that my cutoff frequency FC is about 159.15 hertz, alright. This is also is there. Let me again write it down clearly, so you get it here. Here my FC equals to 159.15 hertz. Okay. So, having this particular conditions, if I make a RC filter, this is passive, right, passive low pass filter, what kind of voltage I get and what is my waveform or shape of the output signal. I have to see two things. So, let us see now again we are taking help of Sitaram. So, he is connecting the resistor and capacitor in series. As you can see, you focus on this one C and R, you can see very clearly C and R are in series. Now, you see the resistor, the input should be given to the resistor and the ground should be there. So, there is a ground which is black wire. Okay. So, now we have a black wire which is ground, the signal is given through the red wire. Now, we are giving signal to a function generator and we will be able to see the output voltage on the oscilloscope, alright. We will be looking at the output voltage on the oscilloscope. We will also be looking at the waveform or the shape of the output voltage on the oscilloscope. Two things we will see simultaneously. So, now he is applying signal which is 5 volts peak to peak sine wave at 100 hertz, 5 volts peak to peak sine wave at 100 hertz. So, can we see the function generator please for a second. This is 50 hertz, this is 50 hertz, 5 volts peak to peak at 100 hertz. Yeah. Okay, so slowly we are increasing the frequency from 50 to 60 to 70 to 80 to 90 to 100, and we will see what is the change in the output. This is a simple RNC, that is a low pass passive filter, low pass passive filter. Okay. Have you connected the input and output both?
Yellow is input, blue is output.
I cannot differentiate it. Can you just shape it? It is very difficult to see. Can you just move the y axis, okay, so that we can see both the signals simultaneously. Yeah, that is better. You bring the blue down. Okay, that is fine. Alright. Now, what you can see is, if you see the function generator, we applied about 50 hertz frequency at 5 volts peak to peak, and we are looking at the oscilloscope. This is 50 hertz at 5 volts peak to peak. Now, we are looking at the oscilloscope, and in oscilloscope we can see, yeah, on oscilloscope we can see the input as well as output, we can see the input as well as output, right. So, we can see the frequency 50 hertz, it is allowing 50 hertz to pass. So, you can see frequency 1, which is yellow one, which is the frequency from the function generator, frequency 2 is the output of the passive filter, right, low pass filter, and you can see that the output is 50 hertz. Now, let us change the frequency, let us increase the frequency. Okay. So, we are increasing the frequencies to 60 hertz. You can just look at the oscilloscope, he is increasing to 60 hertz, 90 hertz. So, slowly, so 100 hertz, still you can see it is following 119, 120, is still following 120, and now 150, and suddenly you see that the amplitude is getting clipped, or amplitude is decreasing, right. You see slowly and gradually, as you go on increasing the frequency, the amplitude at the output of the RC is changing, is decreasing, is continuously decreasing, and you can see the peak to peak amplitude for the 5 volts input is 1.04. That means, now it is creating a problem for the signal to pass. At certain point, you see 80 millivolts. So, for 5 volts we are not able to see 5 volts at the output, rather we are looking at only 800 millivolts at the output. That is that the role of the RC filter, or you can say a low pass passive filter, alright.